Achha, so AS carbonyl compounds. Now in carbonyl compounds, what you have is that when you talk about carbonyl compounds, carbonyl compounds are stereal bond O. You can have an aldehyde where the stereal bond O is right at the end of the chain, and you've got ketones where the stereal bond O is right in the middle of the chain. So you've got two types of carbonyl compounds, aldehydes and ketones, and they're polar molecules. What that means is that this is a polar bond. The carbon has a partial positive charge, and the oxygen over here has a partial negative charge. This oxygen is also slight negative. This one is slight. It's going to be slight positive. So it's a polar molecule, and its melting and boiling points are going to be higher than. So the melting and boiling points are higher compared to alkanes and alkenes. Compared to alkanes and alkenes. Why? Because they only have van der Waals forces. And but the melting points are lower compared to alcohols and carboxylic acids. I said they're lower compared to alcohols and carboxylic acids. Why? Because they have hydrogen bonding. So the force of attraction is a lot stronger. In those. So it's the melting and boiling points are kind of in the middle. They've got permanent dipoles. The other thing is that we already did when we talked about oxidation was that when you have an aldehyde or a ketone, we earlier did oxidation of aldehydes and ketones. Primary alcohols would get oxidized to aldehydes, and those aldehydes are going to get further oxidized to carboxylic acids. So if you're stuck at an aldehyde, you got two choices. You can either get oxidized to a carboxylic acid, or you could get reduced, back to a primary alcohol. So this one would be reduction. And this over here is going to be oxidation. So for oxidation, you would need you can have three things. One is K2Cr2O7, which is the oxidizing agent, acidified and reflux. Or you could have, that's number one. You could also have the other slightly stronger oxidizing agent, KMNO4, plus reflux. The second one is you can have Tollens reagent. Which is basically Eg silverines with ammonia. So silverines in mixed with ammonia, that's aqueous. And then you've got number three, which is fillings. So you could add Felling's reagent and it will get oxidized plus heat. Now, each one of them is going to have a separate color change. For example, the first one is going to give you a color change, which would be K2Cr27 is orange to green. So each one is going to have a separate observation. KMNO4 is purple to colorless. Tolerance gives you a black precipitate. Or you can say that it gives you, what else you can say is it gives a black precipitate or a silver mirror. Basically, the aldehyde gets oxidized to carboxylic acid. And when it gets oxidized to a carboxylic acid, the silver ions get reduced. They turn back into silver. So which is why you get silver mirror. And then you have Felling's reagent, which is basically, Felling's reagent is copper 2 plus ions. It contains copper 2 plus ions. So it's going to get reduced to an oxide of copper, which is a brick red precipitate of copper 1 oxide. So those are the three reagents that you're going to have. And TK, we already did this. This was the oxidation chart that we did. But we are focusing on the aldehyde. The aldehyde can be reduced as well. It can be reduced back to a primary alcohol by two reagents. One of them is LiLH4 or NaBH4. So it could be reduced back again. And you can turn a primary alcohol back into an aldehyde. How? You can turn it back into an aldehyde by oxidation. You can oxidize it. And when you oxidize it, it's going to turn into an aldehyde back again. So for oxidation, what you would need is K2Cr2O7. Or it could be KMNO4. Not recommended, but that would do the job as well. Plus reflux. So these are the two things that are going to do that. And similarly, an aldehyde could be turned back into a carboxylic. The carboxylic acid can be reduced. It can be reduced back to an aldehyde as well. And for reduction, you would need a LiLH4. So remember this chart that this is the oxidation chart that we did earlier. Primary alcohols turning into aldehydes and aldehydes turning into carboxylic acid. So remember, aldehydes can go back to a primary alcohol. Aldehydes can get oxidized to a carboxylic acid and so on. When it comes to ketones, ketones can't get oxidized. That's one thing. So you can't oxidize a ketone. So you can't oxidize a ketone, and but you can reduce a ketone. So one thing you should remember about this is there is no oxidation. Like no matter what the oxidizing agent it is, it's not going to get oxidized. So no oxidation for a ketone. But it can be reduced back to a secondary alcohol. So it's going to be reduced back to a secondary alcohol. That is possible, and for that it's the same reagents. It's NaBH4 or LiAlH4. So it's kind of the same reagents that are going to be used. And you can oxidize, I mean, I'll just copy paste this. It's going to be the same thing. You can oxidize a secondary alcohol using the same stuff. So that would lead to oxidation. But remember, that would lead to oxidation of secondary alcohols. But remember, ketones are not going to get oxidized. There's not going to be any reaction where ketones are getting oxidized. That is not going to be possible. So then the next thing about aldehydes and ketones is, one is the oxidation part that we already did. The next part about aldehydes and ketones is it's about the nucleophilic addition reaction. They undergo one specific reaction, which is known as nucleophilic. This one is known as nucleophilic addition. Now, nucleophilic addition is a reaction where you have an aldehyde or a ketone. It's both for aldehydes and ketones. An aldehyde or a ketone, it reacts with HCN, and there's a catalyst involved, and that catalyst is NaCN. So you've got an NaCN catalyst, and cyanohydrins are produced as a result. So that's the overall word equation for the reaction. Reacts with hydrogen cyanide and you get a cyanohydrin. So what's happening over here? What is happening is that you've got a carbon with double bond O, that's a carbonyl compound. Whether it's an aldehyde or a ketone doesn't really matter. It reacts with an HCN molecule. And what's going to happen to this HCN molecule is that focus on this carbon atom over here. The carbon over here, a CN is going to bond with it at the bottom. So if you just copy this, so what will happen to this is that a CN is going to get bonded to the carbon at the bottom. The double bond is going to go away. And the O at the top will bond with an H. So O at the top is going to bond with an H. So that is your cyanohydrin. That is known as a cyanohydrin. Cyanohydrin is a carbon atom where it's bonded to an alcohol group and it's also bonded to a nitrile group at the same time. So the carbon, which was the carbonyl carbon, this one over here, it's going to get bonded to an OH and a CN. So this is what's going to happen. First thing, forget the mechanism. Let's learn how to write this, how to do this. Like if you're given a reaction and the reaction has, so the reaction has aldehydes and carbonyl groups. So let's say there's an aldehyde group and there's a carbonyl. This one is an aldehyde, the one at the end. So here's a molecule. And I'm going to react it with an HCN molecule. And you would need two HCN molecules because you got two carbons now. There's a carbon over here and there's a carbon over here. Both of them are carbonyl. They've got double bond O's attached to them. So now what will happen is focus on that carbon atom. The carbon atom which was double bond O is going to turn into COH and CCN. So do this over here. I'm going to change this to, this carbon will change into, it's going to have an OH group attached to it and a CN group attached to it. So this is what I'm going to do. I'm going to change that. I'm going to make this OH. So that's one thing I'm going to do. And I'm going to attach a CN to the same carbon atom. Same thing over here. I'm going to turn this into an OH. So the double bond is going to go. I'm going to turn it into an OH. And a CN will get attached to it. So this is what a cyanohydrin is. The double bond O carbon, when it reacts with HCN, the CN bonds to the carbon at the bottom and the O at the top turns into an alcohol. The H from this, the H from the HCN bonds with the oxygen at the top. Is this clear?
Yes, sir.
So whenever you see this, whenever you see a double bond, or whenever you see an aldehyde or a ketone, the same thing would happen. TK, it's going to turn into a cyanohydrin. Now the other thing is the mechanism of the reaction. Why does this reaction happen, and what's the mechanism? And they're going to ask you about the mechanism for the reaction. So we're going to write the detailed steps now, and they're going to ask you about this. So the detailed step says that if you have a ketone or an aldehyde, you've got a acyl bond O attached to a, let's say I have an aldehyde attached to an H. Now the acyl bond O is very polar, which means that it's got positive and negative charges. So the carbon over here is positively charged, and the oxygen at the top is it's got a slight negative charge. What will happen is that CN-1 ions are your nucleophiles. They've got these lone pairs. They're nucleophiles. Remember, they were nucleophiles in nucleophilic substitution as well. So these are your nucleophiles. The electrons from the CN-1 are going to be attracted to this carbon, which is positive. So they're going to be attracted to this positive carbon atom, this one over here. And as the negative ion over here approaches this carbon atom, the electrons in this bond are going to get, there's negative charge over here, so the electrons over here will be repelled further to the top. So that's the first step. The second step is, let's just copy the whole thing. Now the second step is, that the CN will bond at the bottom. So the CN is coming in. So the nucleophile is now ready. It's going to get attracted to the carbon atom, and it will bond with this carbon atom. And so the CN will join, and it's the carbon in the CN that will join with the carbon atom. The electrons over here are going to get repelled upwards. So the electrons are going to get repelled. So the double bond will turn into a single bond because all the electrons in the pi bond will be pushed to the top. And in the next step, the HCN, the H from the HCN, which was, that is going to be attracted, or it would be attracted to the lone pairs, and it will join with those lone pairs. So the last step is, so it's just a simple two-step reaction whose mechanism should be known. So the very last step is that the H will join with the O at the top. And that would make it an alcohol as well. So it's going to join with that. And that's it. Those are your two steps. Remember this by heart. Remember everything about, there's an intermediate that is formed over here. It's a proper two-step reaction. And intermediate is going to be formed. And always remember that when a CN is attached, one important point about this reaction is, whenever you have a reaction with CN, the length of the carbon chain increases. So the length of the carbon chain is going to increase when you have this reaction. Okay, is this clear?
Yes, sir.
So this is nucleophilic addition. You just have to remember this. You have to remember that what happens when you reacted with HCN. NaCN is the catalyst. Remember, why do you add NaCN? NaCN is a source of, it provides CN minus one ions, because the reaction is started by CN minus one ions. So you need a bit more of them. They're acting as a catalyst because HCN doesn't really ionize a lot. So which is why you have to add some extra CN minus one ions so that the reaction can start. So CN minus one, the nucleophiles, they initially come from the catalyst. From the NaCN. They initially obtained from the NaCN catalyst. Okay, now the thing is, just 1 second. So that's where you're going to get this. Okay, so that's the mechanism. That's about it. That's about all that you need to know about aldehydes and ketones. You need to know their place in the whole oxidation reduction scheme. They're kind of in the middle, and you need to know nucleophilic addition. That's one very important thing that needs to be known. So then you've got got another reaction which is known as the Iodophone test, which is not specific to aldehydes and ketones, but so let's talk about the Iodophone test. So now the Iodophone test is, one second. So Iodophone test is, it's a test for a very specific organic molecule. The molecule needs to have this specific structure. It needs to have a methyl group, which should be next to serial bond O. And whatever comes after this, we don't really care. I mean, so the entire structure must have this partial structure. It must have a methyl next to a serial bond O, and preferably that's a carbon chain or a hydrogen atom. That's it. Or what you could have is you could have another one, which is you're going to have CH3 next to CH and OH, and there's going to be a carbon chain next to it. So that's another one. These two structures, if these two structures are present in any molecule, Iodophone test is you add NaOH aqueous alkaline, sometimes it's written as alkaline, and you mix it with iodine. So that's your Iodophone test. Now in this case, what will happen is that the CH3 is going to it's going to break off in both cases. The CH3 will leave the molecule and it will react with iodine, and it would form a yellow precipitate of this thing. Now this one is called triiodomethane. The rest of the molecule, the remaining part, and focus on this carbon atom, only this carbon atom, this one, which was attached to the CH3, only that carbon atom. So the rest of the molecule, the carbon that's left behind will turn into a carboxylic acid, but it will form a salt of the carboxylic acid because the conditions are alkaline. Since the conditions are alkaline, so during those alkaline conditions, you'll get a salt of the carboxylic acid. That's it. So that's your Iodophone test. So whenever you see this molecule, whenever you see any molecule that has this structure, like if you see a butanone molecule, so an example could be that you have CH3, which is next to acetyl bond O, CH2, and CH3. Now, if you have a look at this molecule, that's an example. What will happen is that during the Iodophone test, this will form a yellow precipitate of CHI3. And the other part, the remaining part of the molecule would be CH3, CH2, and C double bond O and O minus 1. Not the carboxylic acid, but the salt, because the conditions are alkaline. It's NaOH aqueous plus iodine. So during those alkaline conditions, this carboxylic acid would react and would eventually form a salt. Like if it reacts with NaOH, the salt would be an Na salt. It would be Na plus 1. So if the alkali that you're using is NaOH, like I'm doing over here, so it's going to be a sodium salt. So that's your Iodophone test, but the Iodophone test is very specific to these two structures. If these two structures are present, then the Iodophone test is going to be positive, otherwise it's not. Then related to aldehydes and ketones, there's one more test, and that test is used to identify carbonyl compounds, only carbonyl compounds. And that's a test with 2,4-D and pH. So you have a test called 2,4-D and pH. It's a test for identifying aldehydes and ketones only. Any aldehyde or ketone. It's a test, a very specific test for identifying aldehydes and ketones. Now with 2,4-D and pH, first thing, what's the name? What is it? What is this structure? This is called 2,4-dinitrophenyl hydrazine. As it's called 2,4-dinitrophenyl hydrazine. That's the name of this molecule. The molecule looks like this. The molecule has, so let me, so it's got this benzene. This ring molecule is a benzene. And this molecule over here, one second. It's no idea what's happening. Just a second. So it's got N, another N, NH. You kind of have to remember because they sometimes do ask you to make an equation for this. It's a simple test. NO2, but the molecule is kind of complicated. So you have to remember what the molecule looks like. They've asked you in the past papers to actually make equations with 2,4-D and pH when aldehydes and ketones react with it. The shorter formula for this is this one is known as C6H3. You got two NO2s attached to it, and there's NH and NH2. So that's the condensed form of this 2,4-D and pH. Now, when you react it with an aldehyde or a ketone, this is what will happen. That here's an aldehyde, a carbonyl group, double bond O, and H. So this is what happens. The hydrogens and the oxygen over here, they react together to form water, and it's a condensation. It's a type of a condensation reaction that actually takes place. And the two molecules kind of, they get together and they join up. So in the middle over here, the two molecules are going to join up, just like esterification, like any condensation reaction. The oxygen will be gone. The H's will be gone. There's going to be an H, and this carbon is going to come to, the two are going to come together, and they would end up forming a double bond in the middle, and they're going to join up. And this is going to give you an orange precipitate. So whenever you have aldehydes and ketones, the result is, the test result is that if you want to identify an aldehyde or a ketone, you add 2,4-D in pH. And when you add 2,4-D in pH, which is this thing, you get an orange precipitate. Now one thing is, it's up to you. You can either try and remember the reaction, which would be pretty hard to remember actually. The other option is you can actually leave the reaction, like forget the reaction. Just remember that the test for identifying aldehydes and ketones is 2,4-D in pH. And what you get out of that is an orange precipitate. So whenever you have an aldehyde, add 2,4-D in pH, you get an orange precipitate. So that's the basic thing. That's the minimum thing that you should remember. Only once have they actually asked for the whole reaction. Only once in like 10, 15 years, there's only one question where they've actually asked for the whole reaction. So it's good if you're able to remember the whole reaction. But in my opinion, it would be kind of a waste of time because there's a very high probability that's never going to be asked. So the minimum that you should remember is to test for an aldehyde or ketone, add 2,4-D in pH, and you will end up getting a orange precipitate when you do that. And at least remember the formula. Like, I mean, you should be able to, by looking at it, you should be able to remember what this is. So that's an aldehyde and a ketone. So with this, we're pretty much done with. The only thing that's left is carboxylic acids. And there's not a lot in carboxylic acids to begin with. I mean, for example, it's actually not this syllabus. You're actually on the syllabus. So carboxylic acids. Nothing kind of new with carboxylic acids. Like if you have a look at the syllabus, where's the most of the dark one, that's an A2. So you don't have to do all of that. Amino acids, primary amines, etc. Everything is A2. Esters, that's O levels. We can go through that. Carboxylic acids, again, mostly it's esters. We've actually discussed the reduction of carboxylic acids before. So that's done. You just need to know that carboxylic acids, that's also oxidation. I mean, we just did this. Like carboxylic acids are kind of already done. Even in aldehydes, we did carboxylic acids, like over here. We did this part. That primary alcohols get oxidized to aldehydes and aldehydes get oxidized to carboxylic acids. So we did this. Carboxylic acids, they get reduced back to aldehydes by ALH4. So that's kind of also done. So we'll just quickly go through the reactions with metals, alkalis, and carbonates. We can kind of go through that. But most of the other stuff is done. We can do ester formation. That's also part of O levels. But what we'll focus on is past papers now. Okay. So I'm actually done with the O levels paper. So I've got a lot of time now. So I'll try and have a past paper class at 9:30 now. Okay, today 9:30 I'll have a past paper class. We'll just do organic past papers. If you want to do some other past paper, we can cover those as well. Okay. So in 1.5 hours, but make it 9:40 actually. Okay, so we'll have a past paper class. I'll message you for that. Okay. Okay, everyone.
Okay, Allah Hafiz.
Take care.
Thank you.
Allah Hafiz, sir.
Allah Hafiz.
Allah Hafiz.